In this presentation, we are going to look at the non-parametric procedures. Okay. So what we're going to do here in the first part is the definition type question. Discuss the advantages and disadvantages of using non-parametric rather than parametric methods in statistical analyses. So, parametric methods require a distributional assumption, often the normal assumption, to be specified as a model for the observations. That is to say, we assume that the observations are normally distributed or the variable of interest is normally distributed and so on. Now, if that's not correct, inferences, and here inferences means hypothesis tests, confidence intervals, any sort of conclusion drawn upon those can be seriously affected. Okay, so we might reject a null hypothesis where we should have failed to reject it and so on. Okay, so essentially because these inferences, these procedures are based on the assumption of normality, that the data is normally distributed. Now, non-parametric procedures rely only on such things as the rank ordering of data, okay, and require no distributional assumptions, okay. So we don't sort of assume they're Poisson distributed or normal distributed or anything like that. We just sort of work on the basis of the rank orderings of the data, and no matter what type of data you get, you should have some sort of rank ordering or some characteristic like that in the data that you can build a test upon, a non-parametric test. They allow more general types of analysis, but not based on the means and variances, which are the parameters which give the name parametric methods and non-parametric methods their names. Okay, that's where it comes from, but are less powerful than the parametric methods when they are both available for the corresponding problem. That's quite important. Non-parametric methods are far less powerful. They're less beneficial for overall analysis as opposed to parametric methods. So they're the poor relation, so to speak. So here's a worked example, and I'm going to go through this very quickly. The weights of fish in two populations were compared by analysing the differences in the weights of a random sample of fish from each population matched by length. So it's paired data here essentially. Okay. The weight differences in grams for the 10 pairs of fish were as follows: 12 minus 13 minus 125 minus 120, 2, 3 minus 147 minus 12 minus 4. Okay? So explain why a parametric test would be unsuitable for comparing these weights of the fish using these for these two populations. And then analyze the test using a procedure which ignores the magnitude of the differences, and then another one that uses both the signs and the magnitudes. So essentially, in the first case, it's subtly telling us to use the sign test, and in the second one, it uses signs and magnitudes, which is the signed ranked test. Now, the signed test, first off, the data is very skewed. Okay, you can just sort of tell by comparing a couple of numbers here: minus 125, minus 120, minus 73 versus 2, 3, minus 12, 4, and so on. Okay? So it's not that it's skewed, it's just probably, it is skewed, but it's obviously not normally distributed. Okay? Now, something I should mention here is probably, if applicable, and in this case, the logarithmic transformation wouldn't be applicable in many cases, but if applicable, it might not get the data to the state where you can do a parametric test. Also, yeah, so it doesn't work in each case. Actually, this is well worth a discussion in its own right, non-parametric procedure, the logarithmic transformations. But I'll move on. But just actually, that's well worth remarking upon, particularly for this sort of thing here. So it's a video worth a video in its own right. Okay. Now, a sign test use only the fact if it only is based on the fact if a number is positive or negative. Okay, and how many of them are positive and how many are negative. So in this case, we only have 3 positive differences and the rest are negative differences. So 3 positive, and 7 negative. So if the populations are the same, the null hypothesis says that the proportion of positive signs is 1/2 And essentially what we're dealing with is a binomial variable with mean equal or n equal to 10 and p equal to 1/2. N is the number of trials, p is the probability of success. Okay, now that is constructively what the null hypothesis is. So essentially what we're going to do here is calculate a p-value. Okay, so this is calculated p-value. Calculate how many, the probability of less than or equal to 3 positives, given that it is a binomial random variable. Okay, so p0 plus p1 plus p2 plus p3, and working that out, that is 1 over 2 to the power of 10 times 1 plus 10 plus 45 plus 120. I'm going to sort of skip over that. Really, I have sort of done this calculation with the same sort of numbers in a different video, and we actually get the same p-value there, 0.172. Okay, now the conclusion is that this p-value is greater than 0.05, so it does not provide any evidence of differences, okay, between the two sets of weights of fish. Now this test does not provide it, okay, that's important. The reason is it's not a very powerful test, to be honest with you. Now, just actually, I'm sort of scroll back up here, and this is a sort of complementary test to a presentation to one I've done previously. And essentially what I'm doing at this one is I'm using a programming language called R, okay, to come up with these calculations, just to sort of speed things up. Particularly this one here. This is how I calculated my p-value. Or I checked this, 0.1718, okay. And I used this bit of code here to get it, okay. Now, that's essentially, this is just a sort of complement to how I dealt with this question in another video. So essentially, you can use the R programming language, okay. I'm just going to pop it up there on screen for a second. Okay, I just typed it in there, so that's just me doing some other calculations. But essentially, that's me just doing a couple of other calculations regarding statistics there. So they are programming language, so it's worth getting the hang of that. Okay, just to sort of speed up your calculations on stuff like that. 0718. So that's the sign test. Let's move down to the next one part here, which is the Wilcoxon signed rank test. So we're asked for two procedures, and the second procedure we're asked to use is one that uses both the sign and the magnitudes. Under the null hypothesis, the populations are the same, which is to sort of say one fish is not particularly different from the other fish in terms of weights. And the alternative hypothesis is that the populations are different, as that one is different from the other, greater than or less than or so or whatever. Now, I have done this procedure before, so again, I'm just doing in a different video, so I'll just go over it briefly. What we have here is the absolute difference of the 12 of the fish, okay, the 10 fish, okay. So the absolute difference, and I also have them sorted in ascending order, okay. So they go from smallest to largest there, okay. And you notice I do remove the signs. Now, something I actually do keep track of down here is I do keep track of the sign. So this is the pluses here, and the rest are the negative values. So I keep that recorded, okay, in the table. I've actually sort of distilled it down here. This actually does require a bit of cross-checking in terms of numbers, okay. Now, essentially, I'm going to go from lowest to highest in terms of ranking. So 1 here is the lowest rank, okay. 2 is the second lowest. 3 is the next lowest. 4, it would be the next lowest. Except what we have in this case is a tie here. So this would be the 4th and 5th rank, nominally, okay. But because they're tied, what I'm going to do is I'm going to give them both the ranking of 4.5, which is 4.5. We've no more ties, but that is what you do. And in fact, in some other videos, there are more tied scores. Okay, so 6th, 7th, 8th, 9th, and 10th in terms of ranking, where 10 is the maximum. Okay, now what I'm going to do now is calculate up the rankings for the positive ones and the negative ones. Okay, so if I add up the rankings for the positive group, okay, I would get 1, 2, and 4.5. Okay, if I was to calculate the negative ones, I get 3, 4.5, 6, 7, 8, 9, and 10, which is pretty 40 something. I don't know. Off the top of my head, I can't remember. But anyway, but it's not what we're looking for. The sum. Well, actually, you should check it out there, but it's clearly, in case it might be smaller than this. Okay, I think it's 47.5. But the thing is, what you're trying to do there is make sure you get the smaller of the two. Okay, and in this case, it clearly is the smaller. So the sum of the positive ranks is 7.5, and that is below the two-sided critical value of 8, which for a sample size of 10, so that the null hypothesis is rejected. Okay, I'll just show you where that is shortly. This is from the tables. Okay. Now, so one thing to remark upon is that we are dealing with a two-sided test, and that comes from up here. Okay. So that means we are using the column that does say 0.05. Okay. So using this test, there's little evidence of differing locations of population values. Okay, so by using the values, more information is available. This is like comparing the Wilcoxon test to the sign test, since the positive signs are attached to values which are numerically quite small. The Wilcoxon test thus gains greater power to discriminate between two sets of data that produced the differences given. So I'm just moving down here to the tables just to wrap it up. And this is the Wilcoxon sign rank tables. Okay. Just as we learned before, we were dealing with 5%, and this is a two-sided tables. Okay, so if you're working with a two-sided test, you just proceed as normal. Okay. If you're doing one-sided tests, you have to adjust your approach accordingly. Our sample size here is 10, so that gives us our critical value there, which is 8. Okay, that's our critical value. So that's just a bit of clarity about where this value here came from. Okay, sample size as n equals to 10, a two-sided test with a significance level of 0.05. And that gave us a critical value there of 8. Okay. Whoops, that doesn't look like an 8. That does not look like an 8. That's an 8 there. Okay. So that was our critical value. So 7.5 versus 8. And in this case, what we want to do is check, is the test statistic less than the critical value? Okay. And in this case it is. So that gives us an indication that there is a difference there. So we'll leave it there.